Problem number 9. A uniform stick of mass m is originally on a horizontal surface. One end is attached to a vertical rope, which pulls up with a constant tension force F, so that the center of the mass of the stick moves upward with acceleration a less than g. The normal force N of the ground on the other end of the stick shortly after the right end of the stick leaves the surface satisfies next conditions. Solution for problem number 9. Here we can write two equations. One equation, net force in vertical direction, and other equation is rotational motion. There are no equation for horizontal motion. So first of all, let's write a vertical equation. We have MA equal normal force plus force F and minus gravity force. That's a vertical equation. Rotational motion. We have two forces which create torques around the bottom left corner of this stick. It is force F, for which we have torque equal FL, where L is the length of this stick, and minus torque created by gravity force, which is mg multiplied by L over 2. And that must be equal I alpha, where I is moment of inertia and alpha is angular acceleration. Now let's write what is a relation between alpha and A. Obviously alpha equal 2A over L, and also moment of inertia for this stick equal to 1/3 ml square. Now we can put these expressions to the second equation for rotation, and we will get expression for force F using acceleration A and acceleration of free fall. And now we can exclude this F from the first equation, put it here, and find that normal force equal 1/3 MA plus 1/2 mg. And now, because we know inequalities for acceleration A, that's greater than 0 but less than g, we finally can find what are the limits for normal force. That will be between 1/2 mg and 5/6 mg. If we check answers, we can see that only B can satisfy these limits. So B is the answer for problem 9. Problem number 10. Which of the following graphs best shows the acceleration versus time of an object originally moving upward in the presence of air friction? Solution for problem number 10. Initially, when object moving upward, there are two forces acting on it. That's a force of gravity and also force of air friction, which is going the same negative direction. It means that the original acceleration must be less than g, which is less than negative 10. And finally, when object reaches the terminal speed, acceleration must approach 0. On this graph, we see that only on graph E we have such behavior for acceleration. In other cases, we don't see any terminal speed behavior. And also on graph E, we have initial acceleration is less than negative 0, and it's constantly increasing, which is correct. So the correct answer is E. Problem number 11. A light uniform ideal spring is fixed at one end. If a mass is attached to the other end, the system oscillates with the angular frequency omega. Now suppose the spring is fixed at the other end, then cut in half. The mass is attached between the two half springs. The new angular frequency of oscillations is next one. Solution for problem number 11. Let's write the equation for the first case. We can write that force F equal negative kx, where x is displacement, and this force equal ma, and this is the regular equation for harmonic oscillation with the angular frequency omega equal square root from k over m. In the second case, we have two springs, each half of initial spring. It means it has now constant k, which is a double compared to the first string. We have equation F1 equal negative 2kx, where F1 is the force for each spring. And now they act both on this mass, so their force must be doubled. It means that equation will be ma equal negative 4kx and omega 1 equal 2 omega. That's the answer D, which is a solution for problem number 11.